So let's do a little bit of quick review since it's been 2+ weeks since we really thought about chapter 13, right, and gravitation. Okay. Well, then Priya, you can tell me what's that new form that we have for the gravitational force that comes from Newton's universal law of gravitation. Okay, where M1 and M2 are the masses that I'm talking about. They're separated by a distance r. This force is always attractive. And then we were able to do a bunch of things. We were able to figure out how to express the acceleration due to gravity in terms of the mass of a planet and its radius. So again, when your spaceship crash lands, you'll be able to determine the acceleration due to gravity so that you can figure out the escape speed and get yourself off. We also had a new form for the gravitational potential energy, which was what? Priya. Okay, so again, big M, little m, M1, M2, it doesn't really matter. We're just talking about two different masses. You can distinguish them any way you like. R is still the separation. Please note that that gravitational potential energy, number 1, is always negative. And number 2 is a function of the whole system. Okay, so we kind of get lazy and we think about when we drop things that we're talking about the potential energy of the object that we're dropping. But we're really talking about the potential energy of the system that involves the object in the Earth. Okay, and that's even more important when we're talking here. So we'll get to that in a minute. We also talked about Kepler's 3 laws. Kepler's first law says that the planets orbit the sun in ellipses with the sun at one focus. Kepler's second law says that a line connecting the planet and the sun sweep out equal areas in equal amounts of time. Again, watch the recorded classes. And Kepler's third law, which is the one with the equation, tells us that the square of the period is proportional to the cube of the semi-major axis of the orbit. Which means that t squared over a cubed for objects that are orbiting the same central object, like the sun, for instance, are all going to be equal to the same constant, which is 4 pi squared over that universal gravitational constant, and in this case, the mass of the sun. And we did a little exercise where we talked about t squared over a cubed for the Earth would be equal to t squared over a cubed for Mars, would be equal to t squared over a cubed for the Kepler Space Telescope, t squared over a cubed for an asteroid. It will be the same, that ratio will be the same for any two objects that are orbiting the same massive object. You could also say that t squared over a cubed would be the same for the moon and any other satellite that's orbiting the Earth. Okay. When we're talking about the Earth and the sun, I think I've mentioned that astronomers will bend over backwards to make things equal to 1. We will use the funkiest units we can find or invent them. So that what's the period of the Earth? How long does it take the Earth to go around the sun? 1 year. And what is the distance or the length of the semi-major axis for the Earth's orbit? 1 AU, 1 astronomical unit, so that this is equal to 1. That's what we do. We use funky units so that we can make things be equal to 1. Because really everything in astronomy is an estimation anyway. because things are too far away. Okay, so we were looking at all of that, and I think that we were on to page 382, number 57. If somebody would read that for us, please. Okay. Now, this situation is a little bit different. Okay. So I have two stars. But because their masses are comparable, in this case they're equal, these two objects, it's not one orbiting the other. It's that they orbit their common center of mass. And for two objects that have equal mass, their center of mass is in the middle. Okay, so both of these objects are orbiting around this imaginary point in the middle. Certainly. Honestly, initial conditions. That's why our solar system rotates the way it rotates, is because the disk that helped the sun form happened to have rotated that way. Okay, so we know that the separation between these two is the Sun-Earth distance, which means that kind of the radius of the circles these are making is the Sun-Earth distance over 2, right? It is, but I can't really use those units if I'm going to calculate something in a class like this. Because in astronomy, in AP physics, most of the time we're not dealing with millions of kilometers. We're dealing with, things we can see and imagine. But in astronomy, you're always dealing with really big numbers, so you give them other units so that you can wrap your brain around it. Okay. So what are we supposed to find here? Period of revolution. So we're looking for period, capital T. Okay. So when I've got a situation like this, when I've got two objects that are orbiting around each other, when I have anything moving in a circle, what should you think about? What do you know about things that move in circles? They do. But what do you know? What was the first thing we learned about things that move in circles? Centripetal motion. Okay, so I can take one of these objects, and it doesn't really matter which one, because they have the same mass and they're doing the same thing. If they weren't the same mass, then their distance from the center of mass would be different for each one, and that would balance things out. So it still doesn't matter which star I pick, as long as I use the proper measurements. Okay. So what's the force that's causing my objects to move around each other? Gravitational force. And what might be a convenient way to express the centripetal acceleration? So I can't, well, eventually I can. How would you express it? If you are not on the surface of the Earth, you do not use AG. No. Yes, because angular acceleration is increasing in your omega. It's spinning faster and faster. Well, what's the formula for AC? Go with what you know. What do you know? V squared over R. V isn't really going to help me here. Eventually, I want to get to period. What is period related to? Not really acceleration. Let's just go in general. So I can relate it to what? Okay. Okay, so V is equal. So V is equal to what? Let's back up a minute, because that's taken a lot of steps at once, which some of us can do, but I'm not sure all of us are going to follow that this early on a Tuesday. Okay? So I want, this is something moving around in a circle, right? Moving around. So it would probably make more sense to express this in terms of angular quantities than in terms of linear quantities, because this is really a tangential velocity. So what's the symbol that I would use instead of V? Omega. Sorry, I was drawing it. Okay, so what's the relationship between V and omega? V is omega r, so this is going to give me omega r, whole thing squared over r, or AC is equal to what? Omega squared times r. Okay, so I'm going to use omega squared times r. I've got to square both the omega and the r. That's why there are parentheses. Oh, okay. All right, so that's what I'm going to use for my AC. And then we should all have in the back of our heads that omega is related to period, using some of the ideas that Zoe was talking about. Okay. So what am I going to use for FG? The separation, right? RSE. R sun Earth. Oh, it is R squared. Thanks, Priya. Okay, and that's going to be equal to ms omega squared. But what's this r going to be? Yeah, because it's the radius of the orbit, which we already labeled as RSE over 2. Well, they tell us things, like they tell us it's the mass of the sun, which you can look up. They tell us it's the distance between the sun and the earth, which again we can look up. And we know what the universal gravitational constant is too. So what were you going to say? Yep, I can cancel those out. And then since we're all going to make me proud and remember how omega and t are related, I'm going to solve this for omega, or omega squared. So omega squared is going to be 2g mass of the sun divided by the sun-earth separation cubed. And those are all things that you can look up, or things that you know. Okay. And then, how do I get from omega to the period? So, okay, so omega is 2 pi over t. I like to think of it this way: if we assume that these are moving at a constant speed, okay, that their period is constant, then 2 pi is one trip around, right? 2 pi radians. The period, capital T, is the time it takes to go all the way around. So my omega here is really the distance divided by the time. So that tells me that T is equal to what? Well, it's going to be 2 pi over omega. And then we'll have to substitute in. So that's going to give me the square root of 2g ms over r se cubed. Okay. Which you could plug into a calculator, but I feel that's kind of a waste of our time. It ends up being, if you care, about 2.2 times 10 to the 7th seconds, which is about 0.71 years. Earth years. Okay. And that's information that would be listed in the front of the AP exam if you needed that information. Okay. All right. So the last thing that we need to talk about is the energy associated with these orbits. So as we remember that UG is negative G, little m big M over R, where R is that separation between them. So it doesn't necessarily have to be a constant value for R. And if both of these objects are moving in elliptical orbits around a common center of mass, then the distance between them is going to change, which means that the gravitational potential energy of the system is going to change. And if energy is conserved, if the potential energy decreases, what has to increase? Kinetic energy, okay? Which means that the speeds of the objects are going to vary as the objects move through their orbits, okay? So we're going to talk about first a satellite in a circular orbit, and then I'll kind of wave my hands and we'll turn it into an elliptical orbit just to keep things moving along here. Okay, so I've got some big M in the middle. I've got a smaller mass M that's going to rotate, that's going to orbit around. And the radius of my orbit is r. And like I said, for simplicity, I'm going to make this be an elliptical orbit, a circular orbit. And I'm going to say that the mass of my satellite is much, much smaller than the mass of my planet or my star. Okay? And in saying that, I can say I can only be concerned with energy changes for little m. Yeah, because it's so massive. So because it's so massive, if there's a tiny change, whatever change there's going to be in its gravitational potential energy would cause a very small velocity change. Okay. So I know that for this system, the gravitational potential energy is going to be negative big G, big M, little m over R. And remember, we didn't review this earlier, but remember that what we've done is we've changed where U gravitation is equal to 0. And that we say that the gravitational potential energy of the system is equal to 0 when the objects are infinitely far apart. Okay. So that part's pretty easy. What's everybody's favorite formula for kinetic energy? Okay, which means that I need to know what v is, or v squared. But I've got an object that's moving in a circle. And when I have objects that are moving in circles, what do I think about? What? I do, but what else do I think about? I just thought about it when I started the last little demonstration there. What? Centripetal motion. Okay, so there's a force here between my big M and my little m that's causing my little m to move in centripetal motion. So I can say again that Fg is going to be little m times AC. So this is going to give me G, big M little m, over little r squared is going to give me m v squared over r. So my little m's cancel. One of my r's cancel. And I'm left with v squared is g, universal gravitational constant, times the mass of the big object divided by r. Which tells you that the velocity of the object, the velocity of my satellite, my little m, is set by how far away it is from the big M. So the closer a planet is to the sun, so that's going to mean that little r is going to be smaller. That means that v is going to be bigger, and so it's going to move faster. So Mercury has a day, Mercury does actually, but Mercury has a year of 88 days, and our year is 365 days because we're further out. Jupiter's year is 11 years. Well, and that has to do with what the radius is. But the velocity is going to be different. And the velocity is set by where it is, by how far it is away from the object. So if somebody asks you, if somebody says, hey, I want you to put a satellite that has a period of 6 hours, and actually I'm not sure that's possible, around the Earth, how high up does it go? Well, you've got a period. You need to convert that period into a velocity, and then you can solve for what the radius is. It might be. I drew the number off the top of my head, so I'm not saying it's a valid problem. Well, no, actually, because the Hubble Space Telescope orbits the Earth every 96 minutes. Seriously. But it has to do with what height it's at. Okay. All right, so go back. Remember that what I'm trying to find is 1/2 mv squared. Now I've got my v squared, so I have 1/2 m g big M over r. And this looks suspiciously like what? With the letters rearranged a little bit. Not the force due to gravity, because it's not r squared, it's just r. No. What? Maddie? What? No. No, because UG. It's actually negative UG, which tells me that the kinetic energy can be written as negative UG over 2 for a circular orbit. And that's really important. that you remember that that only works for a circular orbit. You'll deal with many things that are circular orbits. It's up to you. I think that this is a pretty straightforward derivation, and I think it would serve you better to remember to start up here with this, because you'd use that in more situations. Okay? So when I'm talking about energy, I'm usually concerned with what the total energy is. So my gravitational potential energy is negative GMM over R. And my kinetic energy is GMM over 2R, right? So what does this give me? Yeah, it's going to give me negative U M over 2R. Which is actually the negative of the kinetic energy. So remember, this is a circular orbit. Okay. I'm going to wave my hands and say, for a satellite in an elliptical orbit, that total energy is equal to negative GMM over 2A. And in this situation, you'd know what the total energy is. You could still find the gravitational potential energy using the formula. And then, as we often do, the kinetic energy would be equal to the total energy minus whatever the potential energy is. Yep. And you can kind of make an argument that what you're doing is, it's kind of, I mean, I'm not even going to try. You take like some extremes and play with it. I could probably figure it out, but it's just not worth it. Okay. R is always the separation between the two masses. So it depends. It will vary. Okay. Whereas in a circular orbit, we took R to be a fixed value. It doesn't have to be. Okay. All right. So I want to look at sample problem 24. I only want to do part A because it's really just the same calculation over and over again. And I don't really see the point. And then I'll give you like a 2-minute break. And then we'll start chapter 15. And that would be lovely if you would read it for us, please. Yeah. Does it tell you what Earth's radius is? Okay. Okay. So to put the satellite at 1,500 kilometers, we need to change what? What kind of energy do I need to change if I need to take it from the surface and put it up to 1,500 kilometers above the surface? Well, I'm changing its potential energy. To put it into orbit and make it move, I'm changing what? Kinetic energy. Okay, so basically we want to figure out what delta U is and then compare it to what delta K is. So delta U is always going to be U final, which is U at 1,500 kilometers, minus U initial, which is U at the surface. So remembering what the formula is for gravitational potential energy, I can factor out G, M, and M, and then I get 1 over 1,500 plus 6,370 kilometers minus 1 over 6,370 kilometers, right? Because, again, I'm going to go back to what we talked about at the beginning of this chapter, that will assume that the Earth is a uniform object, which means I can use spherical shells, and I can say that all of the mass is really concentrated at the center of the Earth. So when my satellite is on the surface, I say that the separation is the radius of the Earth. When it's going to be up at an orbit of 1,500 kilometers, I have to add those together. And of course, what you're going to have to do is convert those into meters before you do the math. Okay. So what I would do is I would assume that m is equal to 1 kilogram. The mass of the satellite doesn't really matter as long as we're consistent with what it is. Okay. I believe that the mass of the Earth, we'll call it, it's not quite true, 6 times 10 to the 24th kilograms. It's like 5.998, but that's close enough. Okay. And then you know that G is 6.67 times 10 to the negative 11th kilogram, or newtons meters squared per kilogram squared. Oh, really? I don't remember it. Yeah. It's, they like to think they're applying things, but they're really not. All right, do this math. Why don't you give us your numbers, though, and then we'll let everybody else. Okay, good. Yeah, probably wrong. So I'll put your you shouldn't have a negative because remember this is going to be smaller than this. So your parentheses should have an overall negative sign, but there's a negative sign out front. So it should all end up being positive. If that's your only problem, I wouldn't really worry about it. Okay. So that gives us what the change in potential energy is. But now we need to talk about the change in kinetic energy to put it into orbit once it's up there. So again, a change in kinetic energy is going to be K final minus K initial. My initial speed is 0. I just put the thing up there, and it sits there. So the change in kinetic energy is going to be equal to the kinetic energy that the satellite has once it's in orbit, which is 1/2 mv squared. But remember that the speed is set by the radius of the orbit, and that this is equal to 1/2 g big M little m over just r, right? And in this case, r is going to be the radius of the Earth plus that additional height from the orbit. And if we make all the same assumptions we made last time, that the mass of the satellite is 1 kilogram, we know what the mass of the Earth is, what g is, and if you convert r, what are we going to get? Let's see what other people got. Gianni got the same thing. So, what was the question? Okay, well, not exactly. That was the way we chose to solve it, but it actually says, does it take more energy to get the satellite up to 1,500 kilometers or to put it into orbit? So it takes more energy to put it into orbit. So the answer to the question is actually no. You need to be careful, especially when you're doing the part 2s on the AP exam, even the multiple choice, that you go back and ask and review what the question is and make sure you're answering the question. Because chances are in your solution, you've started out by writing down a bunch of stuff that made sense to you, that you related to the problem, but you need to make sure that you actually answer the question that they're asking you. Okay?